Today we're going to do some right triangle trigonometry. You may recall from geometry, SOHCAHTOA. That was an abbreviation to help you remember that the sine of some angle is equal to the opposite side length of that angle over the hypotenuse. The cosine is the adjacent over the hypotenuse, and tangent is the opposite over adjacent. Well, now that we know cosecant, secant, and cotangent are the reciprocals of sine, cosine, and tangent respectively, then cosecant is going to be hypotenuse over opposite, secant is the hypotenuse over adjacent, and cotangent is adjacent over the opposite. So let's actually use this. Let there be some right triangle where an acute angle is labeled theta. The side length 4 is opposite of this angle theta, and side length 3 is adjacent to theta. Let's find the length of the hypotenuse and evaluate the 6 trigonometric functions for angle theta. Well, we know from Pythagorean theorem that one leg squared plus another leg squared is equal to the hypotenuse squared. In this particular triangle, that's going to be 3 squared plus 4 squared equals the hypotenuse squared. Well, 9 plus 16 is 25. Square root of 25 is 5. So I can label here the adjacent is 3, opposite is 4, and hypotenuse is 5. Knowing those, that helps me to figure out what my sine, cosine, tangent, cosecant, secant, and cotangent are. If sine is opposite over hypotenuse, I just labeled adjacent, opposite, and hypotenuse here. That's 4 over 5. And since the cosecant is the reciprocal of sine, then if sine is 4 over 5, then cosecant is going to be 5 over 4. Cosine is adjacent over hypotenuse, so this is 3 over 5. And the secant, being the reciprocal of cosine, is going to be 5 over 3. Finally, tangent, opposite over adjacent, so that's 4 over 3. And the cotangent, being the reciprocal, is going to be 3 over 4. All right, but I've got some other rules to keep in mind as well as some other identities. Let's take a look at those. Sines, cosines, and tangents of special angles. Here I've got the sine of 30 degrees is equal to the sine of pi over 6, depending on, whether you're in degrees or radians. Well, that's 1/2. Sine of 45 is square root of 2 over 2. Sine of 60 is square root of 3 over 2, and so forth in this table. This is actually all found in our unit circle. But what I want you to keep in mind is that we see here that sine of 30 degrees is 1/2, and cosine of 60 degrees is equal to 1/2. That's because 30 degrees and 60 degrees are complementary angles. I can add 30 plus 60, and that'll be 90 degrees, which makes the following true then. Sine of 90 degrees minus theta is equal to cosine of theta. Cosine of 90 degrees minus theta then must be sine of theta. I can do this as well with tangent, cotangent, as well as secant and cosecant. Here are some other identities to keep in mind. We already know about the reciprocal identities, but let's also add in here quotient identities. Tangent is sine over cosine. Cotangent, being the reciprocal of tangent, is then cosine over sine. And my Pythagorean identities, sine squared of theta plus cosine squared of theta equals 1. Here we can manipulate these a little bit too and find some other things, such as 1 plus tangent squared of theta equals secant squared of theta, and 1 plus cotangent squared of theta equals cosecant squared of theta. Now, where might I use something like this? Here's an example. Let theta be an acute angle such that cosine of theta is equal to 0.8. We're going to use this information along with our Pythagorean identity to find sine of theta and tangent of theta using trigonometric identities. To find the value of sine of theta, use the Pythagorean identity sine squared plus cosine squared equals 1. Okay, so let's start there. Sine squared of theta plus cosine squared of theta equals 1. Well, if I know that cosine of theta is equal to 0.8, then I can plug that in. This will now read sine squared of theta plus, if cosine of theta is 0.8, then cosine squared of theta, this is going to be 0.8, and then I'll square that. This is equal to 1. So sine squared of theta plus, let's actually find out what 0.8 squared is. 0.8, let's square this. This is 0.64. This is equal to 1 still. Let's subtract 0.64 from both sides. Sine squared of theta is equal to 1 minus 0.64. This is 0.36. And if sine squared of theta equals 0.36, then I can take the square root of both sides to get just sine of theta. So sine of theta is equal to, let's take the square root of 0.36. All right, looks like sine is 0.6. Okay, now what I can do is, since I'm looking for tangent and I know what sine is and I know what cosine is, cosine was 0.8, that's what I started with. Here we just found that sine is 0.6. I can use one of my reciprocal identities. Tangent is equal to sine over cosine. Well, knowing that sine is 0.6 and cosine is 0.8, that means that tangent is 0.6 over 0.8. Plugging that into the calculator, 0.6 divided by 0.8. This is 0.75. So the sine of theta is 0.6 and tangent of theta is 0.75. All right, lastly, here's an application that can actually be used in the real world. Let's say we have someone surveying the forest. A surveyor is standing 50 feet from the base of a large tree. Now, this tree might be too tall for them to measure in some conventional means, meaning they don't have a rope that goes up that high, or maybe it's too dangerous for them to get up to the top of the tree to measure it, something like that. So what we're going to use is some angle of elevation instead. So a surveyor is standing 50 feet from the base of a large tree. They measure that the angle of elevation to the top of the tree is 71.5 degrees, meaning from the ground to the top of the tree, that angle is 71.5, as we see in the drawing over here to the right. How tall is the tree? Okay, well, let's make a triangle out of this. So we've got the height of this tree. Let's call this h. And we've got a hypotenuse here, and then a leg here. We know that this leg is 50 feet, and that this angle right here is 71.5 degrees. We also know that if I'm working with specifically these two legs, this is the opposite side length over this is the adjacent side length. Tangent of theta is equal to the opposite over the adjacent. So in this particular problem, the tangent of theta is 71.5 degrees. This is going to be equal to the opposite side length, I labeled h for the height of this tree, over the adjacent is 50 feet. Well, I'm solving for the height of the tree, so I'm solving for h. H is being divided by 50. I'm going to multiply both sides by 50. Over here, the 50s will divide out, and I'll get h, where the height is equal to 50 times the tangent of 71.5 degrees. Now, it's really important in our calculator that we make sure that we're in degrees. So I need to check on my calculator. I'm going to hit mode, and I see that I'm in radians, so I need to change that. So I go over and I switch this to degrees, I hit enter. Perfect, now I'm in degrees. Now I can simply put in 50 times the tangent of 71.5, and I'll get the height of the tree is 149.43 feet. So depending on the problem, you'll definitely want to make sure that your calculator is in the right mode. Sometimes that problem will be in radians, sometimes it'll be in degrees. But I hope this gives you a good idea of not only how to use right triangle trigonometry, but different applications for it outside of the classroom.